Morning, everyone. I thought we would at least run through a couple more examples for you. I know you're still probably working on the assignment sheet for the volumes by slicing, and maybe some of you want a couple more examples. We're going to try today and run through one where we draw the base, use the base of the solid using the given equations, and then we're going to slice perpendicular to the x-axis to build the cross sections. They'll either be squares, semicircles, or rectangles that are half as tall as they are wide in this one. And then the other one we will try and draw and slice perpendicular to the y-axis for you in this one. So the one we start with today is we're gonna draw a base region where the region is the graph of x squared minus 2 and x plus 4. Now, I think what would be best for you guys to do is just grab your graphing calculator, and we're going to graph those equations. I've got mine right here, and I've already plotted the parabola x squared minus 2, and I've plotted x plus 4, the red line. And so the region between the curves is going to be the base of our solid. And I've already had started, and I found the intersection point on the upper right corner here to be the point 3,7. So the most important for us is going to be x equals 3. And then let's go ahead and find the other one on the left side. So we'll go and find it by tracing over to it. It looks like -2, but we're just going to double check. Yes, it is. So we're going to go from negative x equals -2 to 3. And up here, I'd actually like to just draw a very simple representation of that. There was the parabola that came here. There was the line here. And this is x equals -2. And this is 3. So what we're going to end up doing is, we'll make this a little bigger for you now, is we'll be making slices through this region that are perpendicular to the x-axis. So for example, I might make one right in here. And if we need to find the length of that slice, because that's going to be the basis for the dimensions of our square or our semicircle or rectangle. If it's going to be a square cross section, then kind of coming out toward you guys, coming out of the screen would be a square whose dimensions are the same as the distance across this region here. When we go to do the semicircle, if I were to draw a slice a different place, then coming out of this will be a semicircle, and the distance between these two curves will be the diameter. Okay, so what we need to do first is formulate how to find the area of these cross sections, because in all cases, the volume is simply an integral of the area of a slice dx, because the dx kind of reminds us of the thickness of the slice. So in these small little slices, the area of the cross section times the thickness of the slice gives us the volume, and then integration takes us across. And in this time, it's going to be from -2 to 3. Okay, so for square cross sections, the distance from any point on the line to any point on the curve is the thing that measures the dimensions. And I just simply call that distance S. It's the side length of the square, or it's the side edge of the diameter. So for all of these, if we're slicing perpendicular to the x-axis, the distance there, S, is simply, we're pretty familiar with this already. It's the distance from the upper function to the lower function. So the line is the upper function, and then the parabola is the lower function. We might want to go ahead and just simplify that by removing the parentheses. X plus 4 minus x squared plus 2. And that simplifies a little further now to x minus x squared plus 6. Okay? So if I have square cross sections, the area is simply that distance squared. So the integral that I'm going to solve to find the volume of the square, all the square cross sections, will be the integral from -2 to 3 of that area, x plus 6 minus x squared all squared. And if we wanted to actually find the volume, we could do one of two things. We could just plug this integral into our calculator, or we could take the time to expand this quantity out by multiplying it by itself and then getting an integral we could solve with the fundamental theorem. I think for you guys, the main emphasis here is to set up the integral in good notation, and then when you want the answer, go ahead and type the integral into your graphing calculator and have it solve for what the volume is. Anyway, on to part B. If the cross sections are semicircles, the diameter is the distance from the upper function to the lower function, and we learned that we actually developed this formula ourselves, that the area of a semicircle with a given diameter was pi over 8 times the diameter, which is going to be that quantity s. Again, so the area is pi over 8 times the diameter squared. So the diameter was x plus 6 minus x squared. And then so pi over 8 times the diameter squared ends up looking like that. Notice it's almost the exact same thing as the square cross sections, just with that extra coefficient pi over 8. So the volume of this solid is going to be an integral from -2 to +3. I can put the pi over 8 in the front, and then I'm just going to write in x plus 6 minus x squared, all squared. Once again, if I actually want the volume, I can type this integral into my calculator, and I'm going to have you guys do that when you're working on the assignment sheet. The main emphasis for this example is just to talk about setting up the integral. Okay, the last example is rectangles that are half as tall as they are wide. Let's actually draw a picture of such a rectangle here. So if it's certain distance across, let's call that S this time. In our diagram, that again is the distance of the slice right there. And so then this height would be 1/2 of that. And if you think about the area of a rectangle being base times height, the area of that rectangle would be now 1/2 S times S, which would be 1/2 S squared. So that allows me to find the volume of all those rectangles simply by integrating the area of the rectangles. Again, from -2 to 3. And I can put the 1/2 in the front, and then S squared is the same quantity we had on the other two integrals. Which actually makes it nice if you think about it. If you think about the answer to A and look at the integral we're using in C, if I really wanted the final answer to C, all you'd have to really do is take the answer to A and multiply it on the calculator times 1/2, because the actual integral is the exact same. In fact, I could have done something like that for B. The integral in B is identical other than the coefficient pi over 8. So once you have the answer to A, you could find the answer to B simply by multiplying by pi over 8 in B and multiplying the answer to A by 1/2 in C. Okay, but the main emphasis here is constructing the integral that needs to be solved. Okay, so when you're working on your assignment, go ahead and type the integral into your graphing calculator to get the volume. Let's look at one now where we're going to slice perpendicular to the y-axis. And I'm going to go ahead and just draw this myself this time. So the region we're going to use is based on y equals root x. I'm going to try and draw that over here. Okay, so square root x function starts at 0, 0, and then would go to 1, 1, and then when you go to 4, it's going to have a y value 2, and it kind of bends around like this. Okay, then y equals 0 is the x-axis, and x equals 4 is this vertical line. So here's the region right there. But this time we're slicing perpendicular to the y-axis, which means we're slicing starting at y equals 0 and slicing across, and your slices actually look like this. Okay, so for example, now if I draw a square cross section from here, they're coming out of this region. I'm going to try and draw three-dimensionally here. Whatever this distance is, that's the distances for all the sides of the square. And so we have to be able to measure in this direction this time, which means the right endpoint is a value of x, which I know is going to be the 4. But the left end also needs to be measured in terms of x, and that's based on the curve y equals root x. So in order to measure this point the proper way this time, I've got to solve this equation for x. So if it's y equals root x and I square both sides, it's giving me x equals y squared. And so this point here needs to be named that way, x equals y squared. And now for any given y value, the x value 4 is bigger than the x value on this curve. And so the distance right here, again, we call that s, is going to be the distance from x equals 4 to x equals y squared. We're kind of thinking of this as the upper function and the lower function again. Okay, so, and our intersection points were the origin, 0, 0, and up here, this is the point 4, 2. Okay, so but it's the y values that are important this time. These will all be integrals from 0 to 2, and this is now the area of a slice, but it's going to be in the y direction with respect to y this time. And so notice that our dimensions in this are perpendicular to the y-axis, and they're functions of y, 4 minus y squared. So once again, with the square cross sections, it's going to go 0 to 2. The dimension in this picture is 4 minus y. So the area of a square would be 4 minus y squared dy. And again, if you want the answer to that integral, you can type it into your graphing calculator if you like to get the final answer. For equilateral triangles, again, we could make a slice here perpendicular to the y-axis going across, and then there would be all these triangles whose dimensions are that same length. And we developed this formula the other day too. For an equilateral triangle, the area of an equilateral triangle was square root 3 over 4 times the side length squared. So this integral is now going to be this, 0 to 2. The side length is the 4 minus y squared. So I'm again going to have 4 minus y squared dy. And I can actually plop the root 3 over 4 right in the front. Okay, so again, this integral now will give you the volume of all the equilateral triangle cross sections. And then we've got the semicircle. And again, the semicircle area is pi over 8 times the diameter squared. So this will be an integral that's pi over 8, again from 0 to 2. And the diameter of the semicircles will again be the distance across, and that's 4 minus y squared squared. And this integral should give you the volume of all the semicircle cross sections. Again, if you want the answer to the second two, once you have the answer to A, the integral used in B and C is identical other than the coefficient. So if I took the answer to A and multiplied by radical 3 over 4, it will give me the answer to problem B. And if I want the volume of C, I could take the answer I got from the square cross sections. It's the exact same integral and just multiply it instead by pi over 8. Well, I hope this helps you guys. I'm going to try and check it within you on Friday of this week and see how you're doing before we move forward into the next lesson.